When you interact with the supply chain knowledge assistant, the experience feels immediate and self-contained. You open the application, type a prompt into a clean text box, and an intelligent answer appears on your screen. But beneath that simple input field, there is no single machine generating answers. The application is actually executing a highly orchestrated sequence of data routing, validation, and retrieval, turning raw input into an organized grid of digital actions. This immediate coordination relies on a specific architectural pattern, a modular client-server framework. This particular system is powered by 5 distinct enterprise components: React for the user interface, FastAPI to route the logic, an LDAP server for authentication, Snowflake to store the data, and Databricks for the AI model. A user interface and a raw AI model cannot safely communicate on their own. If you expose an external AI endpoint directly to a front-end browser, your database credentials and internal logic are entirely unprotected from malicious inputs. In modern AI-integrated enterprise software, a robust, secure middleware orchestrator is the absolute requirement. It is the only way to safely connect end users to backend intelligence. To understand how this works in practice, we are going to trace the exact lifecycle of a single user request. We will follow the data packet as it travels across these 5 specific services. Tracing this sequential data flow reveals how the system manages the competing requirements of identity, storage, and external compute. The first component is the React frontend. This is a pure presentation layer that runs locally in the user's web browser. Its only job is to render the login screens and the chat interface. This diagram shows the defining constraint of the architecture. There is a strict boundary between the client on the left and the server on the right. The front end is never permitted to communicate directly with any external database or AI model. If the browser attempted to bypass this rule and query the database itself, it would require storing active credentials directly in the client-side code. This exposes the entire enterprise infrastructure to anyone inspecting the web page. Therefore, direct requests are blocked. Instead, the application relies on the FastAPI backend. This server sits on the right side of our diagram and acts as the business logic brain of the entire operation. FastAPI is the exclusive gateway. Every single string of text, every single user click, and every data payload must pass through FastAPI's validation before it is allowed to touch an external service. Enforcing this strict separation of concerns protects the sensitive backend infrastructure. The user's browser only talks to the router, and the router handles the risk. Before a user can send a chat prompt to the AI, the system faces its first operational hurdle. It must definitively verify who is submitting the request. To do this, the architecture utilizes an LDAP server, an external corporate directory containing active employee credentials. The authentication flow begins when a user submits their username and password via React. React pushes this payload to FastAPI. FastAPI then securely routes those credentials to the LDAP server for a match and waits for a validation response. Once LDAP confirms the user's identity, FastAPI generates a JSON Web Token, or JWT. Think of this token as a temporary digital passport, which is transmitted back and stored in the React frontend. From this point forward, the React frontend must mathematically append this exact JWT to every subsequent chat request it sends. FastAPI intercepts every incoming packet. Before executing any code, it checks the payload for a valid JWT. If the token is missing or expired, the request is instantly rejected. By delegating authentication to LDAP and using JWTs for the active session, the system uniformly enforces corporate security policies without ever hard-coding active credentials into the application itself. With the user authenticated, we encounter a severe technical limitation. Standard HTTP requests and external AI models treat every single request as an isolated event. In a stateless system, the conversational context vanishes instantly. Ask a follow-up question, and the system has no memory of what it just told you. To solve this amnesia, the system implements the Snowflake Data Warehouse as a dedicated, permanent persistence layer. Let's track a new request, an authenticated chat packet carrying its JWT, moves from the React client into the FastAPI router. Before making any calls to an AI model, FastAPI immediately unpacks the payload, extracts the user's prompt, and permanently logs it into a Snowflake table. Simultaneously, FastAPI runs a query against Snowflake to retrieve the historical chat context specifically tied to that user's current session, pulling it back up into the server memory. By offloading conversational memory to a dedicated cloud data warehouse, the backend compute layer avoids storing massive text files locally. It remains lightweight and scalable, while the end user experiences a seamless, ongoing conversation. Now that the server has the user's prompt and their historical context, it needs to generate an answer. A common misconception is that the heavy AI compute model lives directly on the backend server. It does not. The actual intelligence is entirely externalized, hosted by a third-party service like Databricks. FastAPI takes the raw user query and the historical context retrieved from Snowflake and compiles them together to construct a complete, highly specific prompt. This compiled bundle is transmitted out to the Databricks endpoint for processing. Databricks allocates the heavy compute power required by the large language model, generates the text response, and fires the data packet back to the FastAPI router. Finally, FastAPI performs its housekeeping. It logs this newly generated AI response back into Snowflake to close the memory loop, and simultaneously pushes the text across the security boundary to populate the React UI. Keeping the heavy inference externalized on Databricks protects the FastAPI server from compute bottlenecks. It ensures that the router remains free to handle thousands of rapid UI requests without freezing. When we view this complete pipeline in real time, the logic of the system snaps into focus. The client initiates the prompt. The backend catches it and verifies authorization against LDAP and the JWT. The backend drops the current prompt into Snowflake, pulls up the historical context, and delegates the heavy compute out to the Databricks model. The AI answers. The backend logs the finalized record into the database and pushes the text to the user interface. FastAPI operates as a central orchestrator, constantly and systematically coordinating identity, storage, and external compute for every single user interaction. This strict pipeline reveals the ultimate engineering advantage of a client-server architecture: long-term maintainability through extreme modularity. In enterprise software, AI models evolve rapidly. In 6 months, the engineering team will need to upgrade their large language model to a newer version. Because of this design, upgrading the model requires zero downtime for the user. The engineering team updates the external integration inside FastAPI, leaving the front end and database completely untouched. The same principle applies across the board. If the product team decides to launch a native mobile application, they only need to swap the presentation layer. The core logic handles the new interface exactly like the old one. Storage migrations to a different warehouse, or security updates to a new LDAP provider, remain strictly isolated engineering tasks. Updating one component does not trigger cascading failures across the system. True architectural power is found in isolation. A decoupled framework answers complex queries with speed today, remaining flexible enough to integrate the technologies of tomorrow.